So, now I will go and take you through the okay. So, we now calculate the partition function of the system, and you can kindly you just look at it, that we wrote down this ideal gas. So, ideal gas is the total Hamiltonian, is the just kinetic energy. Ideal gas means the particle does not interact with each other. So, we do not have any potential energy. If we do not have any potential energy, then it is just kinetic energy, and kinetic energy means it is just sum over the here as will be shown in this equation here, it is just that. Now, I want to get the, so why that means that I want to get the partition function, and as I have shown, the partition function here is 1 over n factorial, and then 1 over n factorial and h to the power 3n, then dr1 drn, then dp1 dpn e to the power minus beta h. So, this would be the partition function. Now, look at this partition function, there is no interaction. So, position of the atom. So, I have a so this like I have taken a monatomic gas of spheres, and they do not interact with each other like an argon or noble gas in low density. And then interestingly, if I do that, then I can each particle, they do not interact with each other. So, they are completely disjoint. If they are completely disjoint, I can separate them out. That means this integration dr1 and dr2 dr3 are not coupled, dp1 dp3 are not coupled. So, I have essentially n integrations, identical n integrations who are a product, like these are just product. So, then I have to the power n, and then I have h to the power 3n here, and so this is then my partition function, where q is now given by this integration of dpx, dpy, dpz, dx, dy, dz e to the power minus beta h. This is the partition function of a single particle. This is the partition function of a single particle, and then that I can now do, because dx, dy, dz, there is not in beta h, there is no position. So, I can just integrate over dx, dy, dz, and I can get volume V. Okay, this is clear that this volume V comes out. Okay, and then I have to evaluate this integral, which is this Gaussian integral, and I can do that Gaussian integral. This integral I can do because just bear with me for a minute. This is, I know that minus infinity dx e to the power minus ax square is root over pi by a. I know this integral, that integral is used here. Then if you do that, this integral then becomes, there are 3 integrals, there are 3 because dpx, dpy, dpz are independent of each other, because kinetic energy p one particle is px square plus py square ppz square. So, they are again uncoupled. So, 3 Gaussian integrals, and that integral I can do. So, then I know root over this. So, this is 3 of them, and each comes with a root, then and there are 2m. So, 2m goes over 2 pi m kbt, and kbt is there, beta is 1 over kbt. So, when I do that, I get this. So, this is the partition function of a single molecule in ideal gas. This is the single particle partition function, this quantity is a single particle partition function. Okay, so that thing is done. So, then we can now go back and construct the next partition, okay. So, now we got the partition function, and the partition function Qn is 1 over n factorial, and then 2 pi m kbt by h square 3n by 2. This is the partition function. So now we know that from canonical ensemble we have done that in lecture I think 4th or 5th, that free energy equal to minus kBT ln q, this quantity. So now we can put the q, that this q here. So then we get minus ln, these become minus ln n factorial, and these become n, this is q to the power n, this is q to the power n. So n ln q. So and this is trivial, right? This is, that means q n equal to q to the power n by n factorial. That thing is used here. Now we put the value of q there, which we derived before. So we get the ln n factorial, Starling's approximation is made. So ln n factorial equal to n ln n minus n. If we do that, this minus n actually shows up here as a, and we already have v. So q is already have this n 3n by 2. So I bring out that so n, I have n here. So this only 3 by 2. So n comes out. So n kBT here, this kBT, and q to the power n, capital Q is q to the power n, that brings it n. So n kBT ln, then 2 pi m kBT h square 3 by 2 v. This is multiplied by whole thing here v by n, because they separated out ln v, and the one is, this comes from these things. You can just work it out, the basic things which you will find will work it out fine. Okay. So important thing to understand now, that everything is in logarithmic. So I have a logarithmic here. So there will be logarithmic v term, because it is v to the power n. So that comes from the volume integral, and so when I take ln, that part is ln v to the power n. So that becomes n ln v. So now I can calculate from here the pressure. I can calculate the pressure from here, and that is by thermodynamic relation, pressure minus dA dV kBT, and then you can do that. Look at the, let us do these things here. So this is ln. So then I break it out, I like ln this term plus v by ln. So it's just ln v dA dV, then that n is there. This just goes out, and I get the 1 over v term, the ln v. So d dV ln v 1 over v. So n kBT in front. So n kBT by v by doing the derivative, then PV by n kBT. So this is the ideal gas law. So now I have a microscopic derivation of PV equal to n kBT, which was surmised by doing experimental, enormous amount of experimental studies, and also what comes out from Maxwell-Boltzmann's kinetic theory of gases. But here there is no kinetic theory of gases, no collisions with the wall, no cross section that we have done. You have to do the collisions of the wall with the kinematic description. We did not do any kinematic description anywhere. We did have a kinetic energy, of course, but we do not have a kinematic description. But this is very important to understand, that this is the pressure of the system of molecules, which is contained in a volume V. This is really magical, this derivation. Next, what goes on, something even more magical, and that is the now we are doing something really very important, and this is something, one of the major reason of reviewing this class once more, and also we will do that in the diatomic gas also. There are certain very far-reaching consequences, and we don't well, actually this kind of jumps at you, that it comes from almost nowhere, because we didn't expect such a beautiful relation so early in our derivation or study of for such a major area of research, such a formidable area of research, like in in statistical mechanics, which is actually, as I told you again, is one of the two major disciplines of our thinking, our theory, our understanding of huge number of phenomena. The very first class I spent fully on describing that thing. Okay. So, now we have the partition function, and now we have the free energy, because we have the free energy A equal to we have this beautiful relation now I know entropy, because I know entropy by this. I know entropy A is equal to minus dA dVt. I have a Qn. I know the Qn, because I know Qn is 1 over n factorial h to the power 3n small q to the power n, and small q I know is 2 pi m kBt. Three by 2 and volume V. I know everything. So I know Qn, and small q is the single particle, and then I know free energy exactly, and then I know that I can now calculate entropy. I can calculate an absolute value of the entropy. It's very important. Thermodynamics cannot give me. Now, yes, you can say, okay, I can get it from ideal crystal, all these things, but this is okay, but you know, everything has to be done numerically. Now I can do that, and the beauty of this thing is now that if I do, I take, now look at this, I take Qn, I take ln of this thing. Now look at that. So if free energy has temperature in two places, one is in temperature T, one is temperature T, this is one, another place it has is in temperature T here in small q here. So when I have to take this derivative, I have to take care of this temperature and I have to take care of this temperature. Okay. Now I do that. First one is easy, dA dt, just this goes off. I have kBt ln q n TV, and this is my q n TV. Great. That's why 2 pi m kBt by h square, all these things come in. Wonderful. Now I have to do the second derivative. That now kB, I don't hit kB with dt the kBt. I come here and do the derivative here. Okay. Now, as I told you, it is not q to the power n. So n comes out. I have a small q, and I have to take temperature derivative of the small q. Okay. Then ln q. So then I do ln q, then ln 2 pi m kb plus ln t. I have a kBt sitting in front when I do that. Okay. So now I can take that derivative, I can do this derivative on this quantity, and I can then I combine the terms. This you can do yourself, and is left as an exercise. You can do it yourself, and you will get that entropy. Just do it yourself, it just takes a couple of minutes. Then you get that this quantity, this entropy. So this part, temperature part, is ln q, the ln is here and q is here, 2 pi m kBt, and that is the volume V. This volume V is here, V by n, and so everything remains the same except E becomes 5 by 2, because one extra terms comes in. 3 by 2 n comes, because this derivative, this 3 by 2, that comes out. So then that T3 by 2 here. So when you take the derivative of that, then 3 by 2 comes out and T becomes half. The T becomes half, then you have a T to the power this becomes T to the power half. You have the T here. So, you combine that T with the T to that becomes half here after taking derivative. So, that becomes T to the power 3 by 2 again. So, you combine get 3 by 2, you are left with one 3 by 2 term, that your one term you combine and get e to the power 5 by 2. So, the main thing is to combine and you can get that term. So, this is the then this is an exact expression for an entropy, a highly non-trivial equation, which is this thing, that entropy of n number of ideal gas law is n kb ln 2 pi m kbt 3 by 2 kbt by v. Now, this v by n one can use now PV equal to n kbt, ideal gas law PV n kbt, and then you remove V by n, bring it here, so it becomes kbt by p. This is more useful because most of the time we want at a constant pressure, not at constant volume, and we know the number of particles, and if we know, and at temperature, constant pressure, constant n. So, this is more of an experimental thing. Then this is an exact expression of the entropy of the system. Beauty of it is the following: the V by n that comes here when you do the calculations is a very is an important thing. It is very important to understand that what makes everything an extensive quantity. So, the entropy that I have here is just entropy is proportional to n, as it should be. Everything else inside is an intensive property. The temperature is intensive property, pressure is an intensive property. So, the entropy is extensive because it is proportional to n. But this is the beauty of an equation. It is called Sackur-Tetrode equation. Sackur-Tetrode equation called a it is often called ST equation. This is the equation which is one of the. So, you now the basic idea of my telling all these things again in great detail is to give you an idea how the statistical mechanics flows. Just like in quantum mechanics, you do particle in a box, you learn that how you solve Schrodinger time independent Schrodinger equation by putting boundary values, and when you do that, lo and behold, discrete energy levels appear, and then you immediately find an use of that particle in a box in explaining the spectra of butadiene or conjugated polymers. Then you go harmonic oscillator, and lo and behold, you can get some idea of the vibrational spectroscopy. Rigid rotator, you get rotational spectroscopy. Those are very preliminary, very simple things that we solve time independent Schrodinger equation, but we get back huge amount of information as if without doing any work that you are getting such formidable and very fundamental things. This is essentially analogous to particle in a box or harmonic oscillator. We will use harmonic oscillator immediately now, but important thing to know that we are getting PV equal to n kbt. We are getting an expression, a beautiful expression of entropy, an absolute value of entropy, although ideal gas, but it will find a lot of use. Even today, this research, this equation finds a lot of use. So, next what we will go, we will do the okay. So, one can now calculate the translational entropy. This is called translational. We have taken all the translation into account. So, entropy, the values of the absolute value of the entropy. See, in thermodynamics cannot give you absolute value of the entropy. Absolute value of the entropy, this is the neon, argon and krypton in atmospheric pressure, but then atmospheric pressure of course is probably not a, but whatever condition is not written here, I do not remember, but the experimental condition that we can calculate this translation entropy of the particle, then we can an experimental way of finding the entropy, and it agrees with the experimental values of these this entropy of these three gases, they are very similar to each other. So now I just want to tell you why these things are so important. And so what are the Sackur-Tetrode equation? One of the important applications of Sackur-Tetrode equation of modern times is this quantity, which is the very recently this has been used by several people, that you want to calculate that how a drug goes into minor or major groups of DNA, and that is very important to know, because of many chemotherapeutic drugs, they go and bind to many other drugs, bind to DNA is the target of many therapeutic studies. And so we need to know what is the binding energy of this molecule, drug molecule. This is now done in the following way, that you consider your drug molecules is a the drug molecule is going to go and bind to minor or major group of the DNA. So now this has a lot of entropy in the ideal when it is in solution. Now in the solution we can treat it as an ideal gas, because a single DNA molecule or very low density, a single drug molecule or very low density drug molecule that goes and combines to these to the DNA. So that we need to know the entropy, loss of entropy of the drug when it binds there. So we need to know what is the entropy of this molecule in solution. That is why Sackur-Tetrode equation is used. Then you want to do, for example, gas liquid nucleation. In a low temperature, a gas is going to go to bubble, to form a bubble like in atmosphere, to form nucleation. Then one need to calculate how much entropy the gas particles are losing in order to form the bubble, because once form a bubble, it moves very slowly and it moves as a one particle. So n number of gas molecules like water forms and goes from the water droplet, then it is a huge amount of loss of entropy. So that actually resists formation of the droplet, formation of the cloud bubbles. And particularly that is why high temperature, when these water molecules are still there, but they have a lot of entropy and they will not form the bubble, they will not nucleate. They will not nucleate to form a water droplet which can form as a rain. So entropy of these water molecules in the gas phase, it is not just translational entropy, this is a rotational entropy, it is a vibrational entropy, we will talk of that. So all those entropies play a very important role. So this is done by this gas liquid nucleation, is a huge area of research, and in the study of this nucleation, again this entropy, this in the nucleation theory, again this entropy that we derive today finds use. Now finally, to end this part, that specific heat we know 3 by 2 R, and that is very trivially derived now. If you can go T CV T ds dt, you go to Sackur-Tetrode equation, do the ds dt, then you will find that it just becomes 1 over n kBT by T, that T cancels, and you get CV equal 3 by 2 R, and that is one of the PV equal to RT, along with the ideal gas law. CV equal to 3 by 2 R, and CP is 5 by 2 R, and that is because another way to derive is E equal to 3 by 2 RT, that you know. Then dE dt is CV, this is CV, and that is 3 by 2 R. That is the derivation that from ideal from the kinetic theory of gas, but this is the derivation here coming from entropy directly with the entropy. So it is an alternate derivation, same result, and since equipartition theorem is involved, I cannot say it is more fundamental, because equipartition theorem is as fundamental as the gate, but this is a statistical mechanical derivation with starting from partition function. So this is about the ideal gas law, monatomic gas and ideal gas law. that I wanted to do again in order to take you through a second time the things.